Hello guys, welcome back to my channel. Please remember to like and subscribe. Now today we're going to be looking at the properties of products and quotients of complex number through the polar form. And before you watch this video, please go back and look at my video on polar form and on polar coordinates. So let's get right into it. Let us say that we have two complex numbers. The first one I'm going to call it Z1, which is equal to R1 into cos theta 1 plus I sine theta 1. My second complex number, Z2, is going to be R2 into cos theta 2 plus I sine theta 2. Now what we want is Z1 times Z2, which would imply all of this, R1 into cos theta 1 plus I sine theta 1 times R2 into cos theta 2 plus I sine theta 2. Now, since we're taking the product here and we have R1 and R2 outside of the brackets, we can put those two together. So we could actually go, so this would imply R1, R2, I'm going to open a big bracket, and I'm going to say that this is going to be cos theta 1 plus I sine theta 1, all in one bracket, multiplied by cos theta 2 plus I sine theta 2. Now, we have R1 and R2 outside already. Inside, we're going to expand these brackets just like how we'd expand two normal polynomial brackets. So outside we have R1, R2. Alright, we can clear the innermost brackets now. So cos theta 1 will multiply each thing in the second bracket. So I'm going to have cos theta 1 times cos theta 2, which is really going to be cos theta 1 cos theta 2. Now cos theta 1 times I sine theta 2, I'm going to have plus I cos theta 1 sine theta 2. Now we're going to do the same thing with the I sine theta 1. It is going to multiply everything in the second bracket. So I'm going to have plus I sine theta 1 cos theta 2. And then of course we're going to have I sine theta 1 times I sine theta 2. Now of course I times I is I square, which we know is going to be a negative 1. So let me get some more space here. So this is going to become minus sine theta 1 sine theta 2. Now if we examine this expansion carefully, we would realize that there are several trig identities that might be coming out as us. Now let us go back to our compound angle formula that says if you have the cosine of A plus B, when I expand this, it becomes cosine A cosine B minus the sine of A, the sine of B. And if I have the sine of A plus B, when I expand this, this is going to be sine of A cosine of B plus sine of B cosine of A. Now let us go back to our bracket and see if we can match anything. Now notice in the bracket we have cos theta 1 cos theta 2. Now if we were to move the sine theta 1 sine theta 2 beside that, it would actually match the compound angle formula for cos. In the middle here we have I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2. That also matches the compound angle formula for sine. So all we need to do is to simply put these two together. So I'm going to put the R1, R2 there. R1, R2. So I'm going to have cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. In the middle, we can factor out the I, so I'm going to have plus I. Right, let me move this over so I have some more space. So I'm going to have plus I. I'm going to have the sine theta 1 cos theta 2. So let me open this. Sine theta 1 cos theta 2 plus sine theta plus cos theta 1 sine theta 2 plus cos theta 1 sine theta 2. And because addition is commutative, I can switch them, right? So the theta 1 matches the A and the theta 2 matches my B. So when I break this down, it's going to become R1, R2. Let me open my bracket here. I'm going to have cos of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Good, so this is what happens when we take the product of two complex numbers. So we can actually make a deduction here that if you have two complex numbers z1 and z2, then we can say that the argument of z1 times z2 is simply equal to theta 1, theta 2. We can also speak to the fact that the modulus of z1, z2 is equal to r1, r2. So this is it. If we have two complex numbers that are being multiplied, and let us say we want to find the argument of that product, then we can find the individual arguments and add them. This should have been theta 1 plus theta 2. So this is theta 1 plus theta 2, that is. So the argument of z1 times z2 is simply equal to the argument of z1 plus the argument of z2. And well. Hello guys, welcome back to my channel. Please remember to like and subscribe. Now today we're going to be talking about the properties of products and quotients of complex numbers. Notably, we're looking at the argument and the modulus. Now, if you haven't, before you watch this video, please go back and watch my previous video on the polar form of the complex number. And we're going to get right into it. Now let us say that we have two complex numbers. I'm going to call them Z1, which is equal to R1 into cos theta 1 plus I sine theta 1. And the second one I'm going to call it Z2, which is equal to R2 into cos theta 2 plus I sine theta 2. Now, what we're first going to be looking at is the product of these two complex numbers. So I want Z1 times Z2. Now, this is going to imply R1, open bracket, cos theta 1 plus I sine theta 1 times R2 into cos theta 2 plus I sine theta 2. Now, notice we're taking the products here. Both R1 and R2 are outside of the brackets, so I can take this out here and say R1 times R2. Now, let me open my big bracket here, because I'm going to have cos theta 1 plus I sine theta 1 times cos theta 2 plus I sine theta 2. So we have two brackets here. Now, this expansion, we're going to treat it just like how we treat polynomials. So we're going to multiply everything in the second bracket by everything in the first bracket. So let me put the R1 and R2 outside first. I have R1, R2 outside. Open this big bracket. The cos theta 1 in the first bracket will multiply cos theta 2. Then the cos theta 1 will also multiply I sine theta 2. So what I'm going to end up with here now is cos theta 1 cos theta 2 plus, if I multiply cos theta 1 by I sine theta 2, I'm going to have cos theta 1 sine theta 2, and I'm going to put the I at the front, right? Likewise, I'm going to take the I sine theta 1 and I'm going to multiply the cos theta 2 and I sine theta 2. So that is going to give me plus I sine theta 1 times cos theta 2 is going to give me sine theta 1 cos theta 2. Now we're going to have I sine theta 1 times I sine theta 2. We know that I times I would give me I squared, and I squared is -1. So I'm going to have a minus here. Now sine theta 1 times sine theta 2 is going to be sine theta 1 sine theta 2. Now likewise, once we expand complex number, the next process is always to group the real parts and the imaginary parts. So I'm going to have back my R1, R2 outside, and I'm going to do some grouping on the inside. So I'm going to have cos theta 1, cos theta 2, minus sine theta 1, sine theta 2. That would be my real part. Now, my imaginary part has the I. We know we have to factor out the I, so I'm going to plug plus I, open my bracket here, and inside of this bracket, we're going to put the imaginary part. So this is going to become, now notice we have cos theta 1, sine theta 2, so I'm going to have cos theta 1 sine theta 2 plus sine theta 1, so sine theta 1 cos theta 2. Good. We close the bracket there. But if we were to examine this carefully, we would notice that there are some trig identities popping up here. So I'm just going to do a little recall here. Now if you look at cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, that would remind you of the compound angle formula for cosine. So let me say, recall that if you have the cosine of A plus B, when I expand this, I'm going to get cosine A, cosine B, minus sine A, sine B. Also, if we look at the imaginary part, which is cos theta 1 sine theta 2 plus sine theta 1 cos theta 2, we would notice the compound angle formula for sine popping up here. So I'm going to have the sine of A plus B, which is equal to sine A cosine B plus sine B cosine of A. So in condensing this formula here, let me move this over a little so we can have some more space. In condensing this formula, what I'm going to end up with, move that again. All right, there we go. What I'm going to end up with is that I'm still going to have R1 and R2 outside. But when I open this bracket, where I have cos theta 1, cos theta 2 minus sine theta 1, sine theta 2, I'm going to have the cosine of theta 1 plus theta 2 plus I. And if you look at the second one, which is the imaginary part, that is a compound angle formula for sine. So I'm going to have the sine of theta 1 plus theta 2. So what can I say here? Now, notice that for this complex number, which is the product of Z1 and Z2, the modulus is R1, R2, and the argument is theta 1 plus theta 2. So here's the deduction that I can make here, and let me change the color for this. I can say that the modulus of Z1, Z2 is simply going to be equal to the modulus of Z1 times the modulus of Z2, which is where we have R1 times R2. What does that mean? If I take the modulus of the product of two complex numbers, I can take the modulus individually, and then I find the product of those two modulus. Or should I say moduli? Likewise for the argument. When I want the argument of Z1 times Z2, what I simply do, and if you notice it's theta 1 plus theta 2, is the argument of Z1 plus the argument of Z2, which is simply equal to theta 1 plus theta 2. So what is it saying? If I want the argument of the product of two complex numbers, I can simply find the argument of each of them individually, and then I take the sum of those two arguments, right? And that is what happens when you multiply two complex numbers. This part here is very critical, so I would actually want to highlight this aspect here. All right. Now, just like how we had the product of two complex numbers, we can also look at the quotient of the two of them. So I'm thinking Z1 over Z2, and we're using the same complex numbers. So going right into it, Z1 over Z2 would imply R1 into cos theta 1 plus I sine theta 1 all over R2 into cos theta 2 plus I sine theta 2. Good. Now, what we can do here is to simply take out the R1 over R2 and have that by itself over there. So right away, we have figured out what the modulus is going to be already. This is going to leave me with cos theta 1 plus I sine theta 1 over cos theta 2 plus I sine theta 2. Good. Now, in my previous video, we had looked at division of complex numbers. So to divide them, we simply rationalize by multiplying by the conjugate of the denominator. As you know, a complex number takes the form x plus iy. And that is how we're going to get rid of the imaginary number from the denominator. So this becomes times the conjugate, which is going to be cos theta 2 minus I sine theta 2 over cos theta 2 minus I sine theta 2. Good. Now, in my numerator, we're going to have to expand that the long way. So let me go back here and put the R1 over R2. So we have R1 over R2 into, or we could even start with my denominator because that's the difference of two squares. And whenever we multiply two complex numbers or two conjugates, whenever we multiply a complex number by its conjugate, that's a better way of saying it. We say it's the real part squared plus the imaginary part squared. So it's going to be cos squared theta 2 plus sine squared theta 2. And of course, sine square and cos square, that's just a short way of saying cos theta 2 all squared. We just shortcut it and we have cos squared theta 2. In my numerator, I'm going to have to go that a long way. So I'm going to have cos theta 1 times cos theta 2. So I'm going to have here cos theta 1 cos theta 2. Then cos theta 1 times negative I sine theta 2. So I'm going to have minus I cos theta 1 sine theta 2. And let me create some space. The I sine theta 1 is also going to multiply each term. So I'm going to have, this is going to be plus I. I'm going to have sine theta 1 times cos theta 2. So I'm going to have sine theta 1 cos theta 2. This is where it gets interesting now. I have sine theta 1 times negative I sine theta 2. Now, I times negative I is going to give me negative I squared. But we know I squared is negative 1. So those two negatives would now give me a positive sine theta 1. So sine theta 1 sine theta 2. Good. Now, we're back to the same point when we were multiplying. Notice here, we are bringing out the compound angle formula. But before I even go there, let us look at the denominator. In this case, we know that cos squared A plus sine squared A is equal to 1. Very powerful identity, right? Also, we'll actually have cos theta 1, cos theta 2. So let me go ahead and regroup my numerator before I move further. So my denominator is 1, so that denominator is actually gone. So we have R1 over R2, open bracket, cos theta 1, cos theta 2, plus sine theta 1, sine theta 2. And that is my real part. Now I want my imaginary part. Now notice I have minus I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2. What I want to do is to turn that around so it's easier to work with. So we're going to do is factor out the I, so plus I, right? Because the thing is commutative, we can turn it around. So I'm going to have the I sine theta 1 cos theta 2 first. So this is going to be sine theta 1 cos theta 2 minus cos theta 1 sine theta 2. And of course, all this would be over 1. So we don't need to put the 1 there. Now this breaks down to give me R1 over R2, open bracket. So cos theta 1 cos theta 2 plus sine theta 1 sine theta 2, that's simply going to be the cosine of theta 1 minus theta 2. That's a compound angle formula for cos. Plus I have, and of course in this case they should have really been, yes, so we have sine theta 1 cos theta 2 minus cos theta 1 sine theta 2. So this would have been the sine of theta 1 minus theta 2. Good. So not much differences in terms of what had happened when we had done the product and what happens when we do the quotient. Because notice now we can actually say that the modulus of z1 over z2 is simply equal to the modulus of z1 over the modulus of z2, which is equal to r1 over r2. And when we speak about the argument of z1 over z2 is simply going to be equal to the argument of z1 minus the argument of z2. And this is really theta 1 minus theta 2. So once again, this part here is very critical. Very important. And we're going to do an example to see that this actually does hold true. So in my example, we're going to do it a long way, and we're going to verify by using the properties here. So let's go right into it. All right, here's an example. Given that z1 is equal to -1 plus root 3i and z2 is equal to 1 plus I, find 1, the modulus of z1 times z2 and the argument of z1 times z2. So we're going to go right into the properties. We know that the modulus of z1 times z2 will be equal to the modulus of z1 times the modulus of z2. Now, this is going to be, how do I get the modulus? And of course, my previous video shows you how to get the modulus. For z1, it will be the square root of -1 squared plus root 3 squared times, for z2, it will be the square root of 1 squared plus 1 squared. This is going to break down to give me the square root of 1 squared plus root 3 squared, 4, times the square root of 2. This is going to be 2 root 2. What about the argument? Now, for me to get the argument, one of the first things I probably want to do is to have my argon diagram so I can have a good idea of what is going to happen. So let me just put a little diagram here. For my first complex number, we have -1 plus root 3i. It's going to be in the second quadrant. So my argument and my principal argument here would be this. Now, since it's in the second quadrant, we know we have to add pi to whatever we get. So the argument of z1 is going to be equal to pi plus tan inverse the imaginary part over the real part. So that's root 3 over -1. This is going to give me pi plus, when I find the root of 3 over -1, I'm going to get minus pi over 3. This is going to break down and give me 2 pi over 3. My second complex number, which is 1 plus I, is in the first quadrant, right? So pretty much we don't even have to draw the argon diagram. Bear in mind we had said that once it falls in the first quadrant or the fourth quadrant, whatever you get inside it, you can calculate it, you can work with it. But just for argument's sake, let me call it Z2, argument would be there. Now, of course, we don't even have to work this out because 1 plus I means 1 to the right, 1 up, which means that the complex number here is going to fall in the center between the positive x-axis and the positive y-axis, which means that the angle is going to be pi over 4. But we can work it out. So we can say that the argument of Z2 is just equal to tan inverse the imaginary part, which is 1 over 1, which is going to be pi over 4. All right. Now, this is what we say. Based on the property, we say that the argument of Z1 times Z2 is simply going to be the argument of Z1 plus the argument of Z2. So this is equal to 2 pi over 3 plus pi over 4. Alright, 2 pi over 3, and this breaks down to give me, this is 11 pi over 12. So my modulus will be 2 root 2, and my argument will be 11 pi over 12. Now, just to ensure that this is actually correct, we're going to be doing it a long way to see if we actually get the same answer. And so we reduce the size so we have some more space. So we're going to have Z1, let me change this here, Z1 times Z2. So I'm going to have negative 1 plus root 3i times 1 plus I. And of course, you know that when we expand in this, so we multiply everything in the first bracket by everything in the second bracket. So I'm going to have negative 1 times 1, which is negative 1. I'm going to have negative 1 times I, which is minus I. I'm going to have root 3 times 1, which is plus root 3I. I'm going to have root 3I times I, which is going to give me root 3I squared. But we know that I squared is negative 1, so I'm going to have minus root 3. Now we always group, so we're going to have negative 1 minus root 3, and then we're going to have plus I, we factored I, we're going to have negative 1 plus root 3. Now, what we want here is the modulus of this. So the modulus of Z1, Z2 would imply the square root of the real part squared. So negative 1 minus root 3 squared plus the imaginary part squared, which is negative 1 plus root 3 squared. Good. Now notice that these are perfect squares. So this is going to break down to give me, I square the first term, I multiply the first term by the second term by 2, and I square the last term. So I'm going to have 1. Negative 1 times negative root 3 times 2 is going to be plus 2 root 3. Then negative root 3 squared is just going to give me 3. Alright, for my second bracket, negative 1 squared is going to give me 1. Negative 1 times root 3 times 2 is going to give me minus 2 root 3. And then root 3 squared is going to give me 3. So notice what is going to happen here. This cancels out this. So I'm going to be left with 1 plus 3 plus 1 plus 3. That is going to give me the root of 8. Now when I rationalize root of 8, I end up with 2 root 2. So right away we can actually verify that my modulus is correct by the property that the modulus of Z1, Z2 is just modulus of Z1 times the modulus of Z2. Because we'd have gotten the same answer here. What about the argument? Now to find the argument, I'm going to have to figure out which quadrant this is in. Alright, we can figure out which quadrant this is in. It's going to be pretty straightforward. What we can do is to factor out a negative. So we're going to have 1 plus root 3 plus I, negative 1 plus root 3. So the real part is negative. The imaginary part is positive. So we know right away that it is in the third quadrant, which is right here, theta. Of course, once it's in the third quadrant, to get the argument, we're going to have to add pi to the tan inverse of the imaginary part over the real part. So we can say that the argument of Z1, Z2 is equal to pi plus tan inverse of the imaginary part, which is negative 1, plus root 3 over the real part, which is negative 1 minus root 3. So this boils down to pi plus, and we can put all that inside our calculators. When I put all of this inside of my calculator, what I end up with is minus pi over 12. Now what is pi minus pi over 12? I'm going to end up with 11 pi over 12. Which of course, when we had used the property, which is the argument of Z1 plus the argument of Z2, we also ended up with 11 pi over 12. So you can see that the property is indeed true. So let's go back and look at it. We got the same thing for the modulus, and we got the same thing for the argument, right? So the property does work. All right, we're going to look at an example with the quotient. So it says, given that z1 equal to -1 plus root 3i, z2 equal 1 plus I, find the modulus of z1 over z2 and the argument of z1 over z2. What I'm going to do is that I'm going to apply the property, and then after I'm finished, you can go ahead and do it a long way and see if you get the same answer. So first of all, from my previous video, it's the same complex numbers, so we can start by saying that the argument, let me go with the modulus first. The modulus of z1 was equal to 2, and the modulus of z2 was equal to root 2. So by the property, we know that the modulus of z1 over z2 is equal to the modulus of z1 over the modulus of z2, which would break down to 2 over root 2, and we don't leave the denominator with surds, so it's going to be 2 root 2 over 2, or we can just say root 2. We can also recall that the argument of z1 was equal to 2 pi over 3, and the argument of z2 was equal to pi over 4. Now, by the property, it says that the argument of z1 over z2 is equal to the argument of z1 minus the argument of z2, which turns out to be 2 pi over 3 minus pi over 4. This boils down to 5 pi over 12. What I want you to do is to divide the two complex numbers first, and then find the modulus and argument of the result, and see if you actually end up with the same answer you should. But bear in mind, whatever you get, it should be the principal argument. So I know that 5 pi over 12 is between negative pi and pi. You should always check to ensure that the argument is the principal argument.